Welcome. Today we are diving deep into the engine room of computer science. We often think of data structures as abstract containers, but they are actually direct reflections of the underlying hardware. We will analyze how the physical realities of the stack and the heap dictate the performance of arrays and lists.
Let's begin with the foundational lie of modern computing, the abstraction of virtual memory.
To a high-level programmer, memory looks like a single, continuous street of addresses. But this is an illusion. Beneath this abstraction lies a fragmented reality managed by the operating system. Understanding this distinction is the first step to mastering performance.
When a program loads, its memory is segmented. We have the text segment for code and the data segment for global variables. Then we have the dynamic regions. The stack grows downward from high addresses, while the heap grows upward from low addresses. In modern 64-bit systems, a massive void separates them, but each region still operates under strict limits.
Now let's examine the stack. This is the region of deterministic memory management, optimized for speed and structure. The stack is fast because it is hardware supported. On x86-64 architectures, specific registers are dedicated to it. The stack pointer, or RSP, tracks the very top of the stack. The base pointer, or RBP, acts as an anchor for the current function's frame. Allocation here is not a search, it is a simple math operation.
Every function call creates a stack frame. In the prologue, we save the previous context and allocate space by simply moving the stack pointer. When the function ends, the epilogue resets the pointer, effectively freeing all local variables instantly. This is why stack memory is self-cleaning and leak-proof.
The stack speed is a result of cache physics. Because stack data is accessed constantly and packed tightly together, it lives in the L1 cache. Accessing it takes about 1 nanosecond. Compare that to fetching from main RAM, which is hundreds of times slower.
However, the stack is finite. On Linux, you typically get 8 megabytes. On Windows, just 1. If you recurse infinitely, you hit a guard page and crash. Also, in multi-threaded apps, every thread needs its own private stack, which puts pressure on your virtual address space.
What happens when we need data to survive beyond a function call or grow dynamically? We enter the heap. This is the Wild West of dynamic allocation.
The heap is managed by software allocators like malloc, not hardware. Under the hood, these allocators use system calls like mmap to request large raw blocks of memory from the operating system, which they then slice up for your application.
When you ask for memory, the allocator must find a free spot. First fit grabs the first slot available, but leaves holes. Best fit searches the list for the perfect size, but is slow. Modern allocators use segregated bins, keeping separate buckets for different sizes, to make allocation effectively constant time.
The enemy of the heap is fragmentation. External fragmentation happens when free memory is scattered in tiny pieces, preventing large allocations. Internal fragmentation happens when the allocator gives you more bytes than you asked for to maintain alignment, wasting space inside the block.
Who cleans up this mess? In languages like C++, you do. It is fast and deterministic, but risky. One mistake means a memory leak. In Java or Python, the garbage collector does it. It is safer, but the collector burns CPU cycles and can pause your program unpredictably.
Now we apply this theory to data structures. The battle between arrays and lists is fundamentally a battle between contiguous memory access and fragmented pointer chasing.
Arrays are the darlings of modern hardware. This is true even for dynamic arrays on the heap. Why? Cache lines. When the CPU reads one integer, it grabs a 64-byte chunk. If you are using an array, that one read pulls in the next several elements for free.
But arrays are fixed size. Enter the dynamic array, or vector. When it fills up, it allocates a larger contiguous block on the heap. Because we double the capacity, resize events happen rarely. Mathematically, the average cost per insertion stays constant, or big O of 1.
Linked lists behave differently. Every node is a separate allocation, scattered across the heap. To find the next element, the CPU must chase pointers to random addresses. This breaks the cache and prefetcher, causing cache thrashing.
Additionally, the pointers themselves consume significant memory.
Let's look at the scorecard. For random access, iteration speed, and memory efficiency, the array wins easily. The linked list only wins in specific scenarios, such as inserting into the middle, but only if you already hold a pointer to that exact location.
With the power of the heap comes the responsibility of debugging. Let's look at how we tame the chaos.
3 bugs haunt every C programmer. Memory leaks, where we lose track of allocated memory. Use after free, where we access data we just deleted. And double free, where we try to delete the same memory twice, often corrupting the allocator's internal structures.
To fight these, we use tools like Valgrind and AddressSanitizer. Valgrind runs your code on a virtual CPU. It is thorough but incredibly slow. AddressSanitizer, or ASAN, instruments your code at compile time. It is much faster and can even catch bugs on the stack that Valgrind misses. In conclusion, the choice between an array and a list is not just an algorithmic decision, it is an architectural one. High-performance software aligns itself with the physical reality of the hardware, contiguous, cache-friendly, and predictable.